Okay, so now after our chart, we're going to draw some pictures, okay? And I'm going to be upfront about the fact that these pictures are very, very bad. They're going to look good right now. Like, you're going to be like, man, I'm really drawing an atom here. But then we're going to get into unit 6 and second trimester, and we're going to learn what atoms really look like. And then you're going to be like, oh my gosh, this is terrible. This is like a preschooler's picture of an atom. And you're not wrong, but right now this is all we know, so that's what we're gonna go with. So if I look at carbon 12 or carbon 13, and we just talked about carbon 12 and carbon 13 up at the top when we were talking about our isotope symbols, right? We had 12 6 carbon and then 13 6 carbon, right? And they each had different numbers of neutrons, though the same number of protons because they were isotopes. Okay, so this circle right here that I am outlining, this is my little nucleus. Okay, so we're gonna draw things that go inside of the nucleus and then things that go outside of it, essentially. So protons. Carbon 6. How many protons is it going to have? Well, if you look at the periodic table, if you've forgotten, it's atomic number 6, so it's going to have 6 protons. How do I draw protons? As these little plus particles. So 1, 2, 3, 4, 5, 6, all mixed together. Carbon 13. How many is it going to have? Draw it. The answer is that we'll also have 6. Then we got to go through and think, okay, well, how many neutrons is carbon 12 going to have? Well, neutrons are mass number minus protons, right? If it has 6 protons, then 12 minus 6 is 6. So it's going to have 6 neutrons, and those are just my little neutral particles. 3, I'm not meaning to draw them smaller, I just didn't leave myself enough room. 5, 6. So that's kind of what my nucleus looks like. Okay, then over here, calculate and draw your carbon 13 neutrons. So it should have been 7. Okay, so you had 6 neutrons on the carbon 12, 6 neutrons on the carbon 13. Now we're down to electrons. How many electrons am I going to have? Well, if I have 6 protons, I'm going to have 6 electrons because I know an atom is neutral. And I'm saying that we're going to have bad electrons because we're just going to draw these electrons out here in a nice little ring, like those planetary orbits that we were talking about. But this is so not what the electrons actually look like. But we are drawing them. They're outside of the nucleus. They have these negative charges. And then over here, since carbon 13 had 6 protons also, it will also have these 6 electrons. So all in all, carbon 12 and carbon 13, they have a lot in common, right? There's not a lot that's different about them. The only thing that's different is their neutron number and therefore their mass. Okay, that's the only difference. So, scrolling down, I've got some kind of challenge questions here. So if you want, you can go ahead and pause the video right now, and I want you to see what you come up with for these 3 questions, okay? Just do your best. I'm obviously going to go over the answers, so just pause the video. Okay, so if I have an atom of potassium 39 and it loses a proton, what's going to happen? Well, if it loses a proton, it now no longer has 19 protons like potassium usually has. It now has 18. And if it has a different number of protons, it has a different atomic number. And if it has a different atomic number, it's now a new element. So now I have argon. And if it once was potassium 39, is my mass number going to change as I go down a proton? Yeah, it is. It's going to go down by 1. So I would have argon 38. Interesting, right? Okay, so what if I have this potassium 39 now and it loses a neutron? If it loses a neutron, will it change its identity? No, because it's not changing its protons. So this is potassium. If it changes its neutrons, is it going to change its mass number? And the answer is yes, again. So this is going to be potassium-38. So lose a neutron, it just becomes a different isotope. Okay? So we can kind of justify that. Or new element, isotope. What about if we lose an electron? This is the one that's extra interesting because we haven't talked about this yet. What happens if we lose an electron? Well, we're not losing a proton along with it, right? Oh goodness. We'll come back to that. Okay, so if we lose an electron, it's still going to be potassium, right? Is its mass going to change? No, it's still going to be potassium-39. So what really changes? What is the electrons don't have mass, right? The only thing they do have is a charge, and they have a negative charge. So if they have a negative charge, then what am I going to be left with? And the answer is, I'm not going to have an atom anymore. I'm going to have what we call a potassium ion. Okay? I am now going to have a charge, which no longer makes it an atom, it is an ion. And if you think about it, if I used to be neutral and I lose something negative, am I going to become more positive or more negative? If I'm losing the negative, I will become more positive. So it's technically a potassium with a +1 charge now as my ion. Okay? And I totally overlooked this, but up on here on the argon, this is going to have a charge now too, right? Because we lost a proton, but we still have 19 electrons, right? So this technically up here should be argon. But if I lose something positive, am I going to become more positive or more negative? I'm going to become more negative. So this would be like argon with a -1 charge, which would never happen, but interesting to think about. Okay? So it's okay if these were a little confusing. They were meant to be challenging right now. Okay? All right. So, heading into this right here. So we talked about the mass numbers on the periodic table being our atomic mass. Or sorry, that was a very confusing way to say. Mass numbers are not always going to match the atomic masses on the periodic table, okay? So essentially this and this are not the same. They will never be the same, okay? The first reason for this is that units for atomic mass are atomic mass units, real descriptive, right? So instead of writing atomic mass units all the time, we abbreviate it as AMU, atomic mass unit, okay? Now the definition of an atomic mass unit is 1/12 the mass of a carbon atom with 6 protons and 6 neutrons, okay? So if you had just a standard atom of carbon-12, you would have the 6 protons, you would have the 6 neutrons. Yes, you would also have 6 electrons, right? The electrons have negligible mass. The protons and neutrons have really similar mass, but not exact. But we're just going to take that, divide it straight down by 12, so that everything is counted as one and the same. And that is the basis for an AMU. Okay? But recognize also that the mass of the proton and neutron is slightly larger and the mass of an electron is slightly larger than 0 also in reality. But this AMU is this kind of relative unit, all based off of this atom of carbon-12. And it's really fascinating. Those of you that will take organic chemistry in college or something like that, you're going to learn so much stuff about carbon-12. Carbon-12 and carbon-13 are the basis of so many different experimental techniques. So the other reason that the atomic mass, what we see on the periodic table, and I'll write that down just in case. Just in case you forget. You don't have to write that down if you don't want to. is because of isotopes, right? And we already kind of defined isotopes. I kind of had these illogically ordered where we're just now defining isotopes formally, but they are atoms with the same number of protons, but different numbers of neutrons, all right? We already talked about that. So their identities are the same. One of them just weighs a little bit more than the other one, stuff like that. So the atomic mass that you see on the periodic table is what we call a weighted average, okay, of all of the different isotopes of that element. Now, weighted averages are kind of like what your grade would normally be in this class, okay? Normally I have it to where 35% of your grade is test and 20% of your grade is homework and 30% of your grade is classwork and then final and whatever. So your points that go into these categories are not all weighted the same amount, right? You go back through and multiply it by this factor of 0.35 or 0.2 or whatever, so that when you add it all together, the different grades that you put in are worth more or less of the overall grade. And the atomic mass is one of these weighted averages too. So when you look at the periodic table, you can kind of tell which kind of elements have isotopes and which ones don't. So look at your periodic table and see which of these have really weird off the wall decimals, right? Like if you look at chlorine, and I don't have a periodic table in front of me, I'm going by memory here. It has 35.45, right? It's impossible for it to have a mass number of 35.45 because you can't have 0.45 of a proton or a neutron. But if you're doing a weighted average, you could certainly come up with something like that. And chlorine does have two very prominent isotopes, which is why it ends up with an average somewhere in the middle. Okay, so to answer this right here, I would say it has an atomic mass in between whole numbers. Okay, so just pretty much everything on the periodic table has an isotope that does exist, as long as you're not getting into the stuff that's radioactive and super big down there. But it'll happen to just about everything. Even hydrogen has an atomic mass of 1.008, right? So it must have an isotope somewhere in there, but you're going to see that that isotope just might not happen very often.